start the class. I will take the waiting list later. I will see the waiting list. Now it's already 6:32. 13 minutes has gone. Now we have to start the class. So this note is just the just a elaborate version of the previous note. That is the note from where we are reading poles and residues. Okay, the note has been given of poles and residues. This note is just the elaborate version of that previous note. No any other, all the contents of this note and the previous note is same. I have just written the problems and the theorems elaborately to for the convenience of teaching. Okay, this note and the previous note is same, just note just has been written elaborately, nothing is different here. So let's start. So for the last couple of classes, we have known about poles and residues. We know how to find a pole of a isolated single, how to check that whether a isolated singularity is a pole or not. And if there is a pole there of a function fz, we know how to find the residue at that pole of that function fz. Okay, now start with a theorem. This theorem is an important theorem, and this theorem is very useful to find an integration of a given function. Okay, this is a chapter of complex integration. We are mainly dealing with complex integration. Our main intention to find the integration of a complex function, and there are various methods. We already known about Cauchy's theorem. Then we know about Cauchy's integral formula, and here is a theorem. This theorem is also useful to find certain integrations. Okay. Now I am going through the statement of this theorem. You go through with me. The statement of this theorem says that if a function fz is analytic everywhere, a function fz is analytic everywhere in the finite plane. A function fz is analytic everywhere in the finite plane except for a finite number of singular points interior to the positively oriented simple closed contour C. So a function fz is analytic everywhere except for some singular points, and these singular points are in the interior of a positively oriented simple closed contour C. Then the value of the integration fz over the closed curve C will be equal to 2 pi I into residue will be 2 pi I into residue of the function 1 by z square into f of 1 by z at the point z equal to 0. Okay, now there are some person in the waiting list. I just take me 2 minutes, couple of seconds to admit them. Okay, so let me elaborate the statement of this theorem. So there is a positively oriented closed contour C. See here the diagram. This is a positively oriented closed contour C. The diagram says that this is a positively oriented closed contour C, and there is a function fz. Fine. There is a positively oriented closed contour C and a function fz. Now they said that fz is analytic everywhere except some points inside C. That is, fz has some singular points inside this closed interval. So these three, there are, I am writing these three. Suppose there are, so fz has some singular points, some finite number of singular points inside this closed curve. Okay, so there is a closed curve C and a function fz. The function fz has singularities, and all the singularities of function fz is in the closed curve C. They said that the function fz is analytic everywhere except some points inside C. So the only singularities of the function fz is inside the closed curve C. This is very important part. So there is a closed curve C, a function fz, and all the singularities of the function fz is inside the closed curve C. Okay, if these three conditions hold, that is, there is a positively oriented closed curve, there is a function fz, and this function fz is analytic everywhere except some points inside C, that is, all the singularities of the function fz is inside the closed curve C. If these conditions hold, then the value of the integration fz over the closed curve C will be 2 pi I into residue of the function 1 by z square f of 1 by z at the point z equal to 0. So, okay, there are three persons. I am admitting them. Now, so there is a function 1 by z square into f of 1 by z. How we get this function? 1 by z square f of 1 by z. We need this function, and then we have to find the residue of this function at the point z equal to 0. So how the function can be find? We know we are given the function fz. Okay, now replacing z by 1 by z in the function fz, we get f of 1 by z. We are given the function fz. By replacing z by 1 by z, we get f of 1 by z. Okay, so f of 1 by z, we have got f of 1 by z. Now multiplying f of 1 by z by 1 by z square, we get 1 by z square f of 1 by z. Okay, so this function 1 by z square f of 1 by z, it is very easy to derive. Okay, now next our uh, the next step is to find the residue of this function, that is 1 by z square f of 1 by z at the point z equal to 0. Now we know the function 1 by z square f of 1 by z. Now we already know how to find the residue of a function at a given singular point. Now if we find this residue, then the value of the integration integral over C fz dz will be 2 pi I into the residue. Okay,
স্যার একজন একটু
so
ওয়েটিং আছে
to this
বলছে
point, হ্যাঁ বলো, আরেকবার বলো।
ওয়েটিং এ আছে স্যার একজন বলছে বারবার
আচ্ছা আচ্ছা, দেখছি। Okay, Ria, Akash, Sharon, and Nilanjit, Rishabh. Please tell them to make their username according to the rule. Ria, Akash, Sharon, Nilanjit, and Rishabh. Okay, now up to this point, if anybody has any problem, he or she can tell me. If you have any problem up to this point, tell me now. So I am assuming that everybody is okay. So we are going to the next part, that is an example using this theorem. So example 8, here we have given a function fz, and we are asked to find the integration of fz over the closed contour mod z equal to 2. We use this theorem, the theorem we have known just now, to find this integration. Okay, now here you can see that the integration may also be found by the Cauchy's integral formula. Okay, the function fz is 5z minus 2 by z into z minus 1. It can may also be found by Cauchy's integral formula, but here we are just trying to give another approach to find the integrals. This is another approach. This is another method or another technique to find the integration. Okay, sometimes you may encounter with such functions for which the Cauchy's integral formula will be a tiresome one or will be a little bit tough. So in that case, you can use this formula, and by using this theorem, the calculations maybe get little bit easier. Okay, so now let's start the exercise. Now here we are here we have said that the function fz is 5z minus 2 by z into z minus 1. We are asked to evaluate the function integration of fz at the point over the curve mod z equal to 2. Now the function fz is 5z minus 2 by z into z minus 1. We can write this function in the form 5z minus 2 by z minus 0 into z minus 1. Okay, fz is 5z minus 2 by z into z minus 1. We can write it in the form fz minus 2 by z minus 0 into z minus 1. So from this function by z minus 0 and z minus 1, we can say that z equal to 0 and z equal to 1 are the singular points of this function fz. From here we can say that z equal to 0 and z equal to 1 are the singular functions or singular points of this function fz. In fact, z equal to 0 and z equal to 1 are the only singular points of this function fz. See, z equal to 0 and z equal to 1 are the only singular points of the function fz. That is, fz is analytic everywhere except at the points z equal to 0 and z equal to 1. Now we will see what is the closed contour, the contour over which the integration we are asked to find the integration. The contour is mod z equal to 2. Now what is mod z equal to 2? Mod z equal to 2 is the circle whose center is at the point origin and whose radius is 2 unit. I am repeating again, mod z equal to 2 is the circle whose radius is at the point 0 at the whose center is at the point origin and whose radius is 2 unit. Now see the diagram. Here we have drawn the closed circle. See, this is a circle whose center is at the point origin and whose radius is 2. And from this diagram, it is clear that z equal to 0 and z equal to 1, that is the two singular points, are inside the closed contour C. Okay, so fz, the function, is analytic everywhere except to the points z equal to 0 and z equal to 1. That is, z equal to 0 and z equal to 1 are the only singularities of the function fz, and these singular points, all the singular points of fz, are inside the closed contour C. Okay, so all the conditions of the previous theorem is satisfied. The function fz is there, the function is analytic everywhere except the points z equal to 0 and z equal to 1, and the points z equal to 0 and z equal to 1 is inside the closed contour C. Therefore, all the three conditions of the previous theorem is satisfied. Therefore, by the previous theorem, we can say that the value of the integration over C will be 2 pi I into residue of 1 by z square f of 1 by z at the point z equal to 0. Here I have written wrong, f of 1 by, this is fz I have written, but it will be f of 1 by z. This is a correction. Okay, so this will be 2 pi I into residue of 1 by z square f of 1 by z. This is a correction. 1 by z square f of 1 by z. So the residue of the function 1 by z square f of 1 by z at the point z equal to 0 into 2 pi I. This is the value of the integration fz dz over the curve C. Okay. Now we have to find this residue. So we are given the function fz. Fz is 5z minus 2 by z into z minus 1. We have to find the function f of 1 by z. So to find f of 1 by z, what we do? We replace z by 1 by z in the function fz. Here we replacing z by 1 by z in the function fz. The function fz was 5z minus 2 by z into z minus 1. Yes, any problem? The function fz is 5z minus 2 by z into z minus 1. We are writing 1 by z in place of z. That is, we are replacing 1 by z in place of z. And after the calculation is here. You can see that we get f of 1 by z is z square into 5 minus 2z by z into 1 minus z. Okay. So by replacing z by 1 by z in the function fz, we got f of 1 by z. Now we multiply 1 by z square with f of 1 by z. And here 1 by z square into the function f of 1 by z. And after multiplying this z square cancel out, we get 1 by z square f of 1 by z, this thing. That is 5 minus 2z by z into 1 minus z. So we got the function 1 by z square f of 1 by z. Now our task is to find the residue of this function at the point z equal to 0. So we are going to the next page where we have find the residue. So now my task is to find the residue of this function 1 by z square f of 1 by z, whose value is 5 minus 2z by z into 1 minus z at the point z equal to 0. Now according to the definition, here z equal to 0 is a simple pole. Now the residue of a residue at a simple pole at z equal to z0 is phi z0, where phi z is z minus z0 into fz. This has already been done in previous class. We have already know how to find the residues. Okay, so I am just repeating. This is a gentle reminder or remember of the previous class. So here we are going to find the residue at the point z equal to 0 of the function 1 by z square f of 1 by z. So this is the function and the residue is z minus z0. Here z0 is 0. So z minus 0 into fz at the point z equal to 0. Okay. So z minus 0 into fz at the point z equal to 0. So this z minus 0 is z actually. This z cancel out and we get 5 minus 2z by 1 minus z at the point z equal to 0. So we are putting z equal to 0 here in the function and we get the residual value as 5. So the residue of the function 1 by z square f of 1 by z at the point z equal to z0 is 5. Okay. So the residue of the function 1 by z square f of 1 by z at the point z equal to 0 is 5. So finally the value of the integration will be 2 pi I into the residual value. So 2 pi I into 5 is equal to 10 pi I. So this is the answer. Now tell me if you have any problem. If anybody has problem, please tell me.
सर वो f of 1 by z का वैल्यू क्या है?
Okay, you are given fz, right? You are given fz. See here, fz. Now by replacing z by 1 by z here, you can find the f of 1 by z. Okay. Suppose
सर ये
here
नहीं सर वो रेसिड्यू फाइंड करने में वो f of 1 by z 0 कैसे हो गया?
f of 1 by z कहाँ बताओ?
तो थर्ड पेज
Okay, going to the third page.
सर वो बॉक्स के नीचे जो है ना रेसिड्यू ऑफ z z इक्वल टू 0 1 by z square into f of z.
Here,
सर वो बॉक्स के नीचे
here.
नहीं सर, वो जो वी नो डैट वाला बॉक्स है ना उसके नीचे वाला लाइन.
कहाँ? फिर से बताओ.
वी नो डैट वाला जो बॉक्स है ना सर,
वो अच्छा
इज अ
अच्छा.
सिंपल. हाँ
That's
उसके
the
नीचे वाला जो
definition of finding the residues.
हाँ तो सर
That
वो
is the
वहाँ पे
that is the residue. Can you hear me?
हाँ यस सर.
Okay, that is the definition of for finding the residues for z equal to z0. Suppose. Okay,
अच्छा.
that is the definition. Just this box is the definition. If there is a simple pole at z equal to z0, then this is the definition of the. This is the way to find the residue at the point z equal to z0.
वो अच्छा.
Right?
यस सर.
You got my point.
यस सर.
Okay, now here for this problem, we have to find the residue at the point z equal to 0. So here z0 is 0 actually. We want to find the residue at the point z equal to 0. Here z0 is 0 therefore.
ओके सर.
Okay, you got my point?
यस सर.
Okay, so I am going to the next topic. So this is Cauchy's residue theorem. Cauchy's residue theorem is a very important theorem of this syllabus. Okay, this theorem is very useful to find certain integration of complex functions. Okay, not only this is very useful to find certain integrations in this syllabus, it is very useful technique to find integrations in your future engineering syllabus. In your future days, you will encounter some functions, some complex functions in your engineering syllabus, hardcore engineering syllabus, where you have to find the integration of that functions using the Cauchy residue theorem. It is a very important technique for the engineers. Okay, so listen carefully for this this part of this lecture. So what is the statement of Cauchy's residue theorem? The statement of Cauchy's residue theorem. Let C be a simple closed contour described in the positive sense. If a function fz is analytic inside and on C, except for a finite number of singular points z equal to zk, k equal to 1 up to n, that is finite number of singular points z1, z2, z3 up to zn inside C, then the value of the integration over C fz dz will be 2 pi I into summation of k equal to 1 to n residue of the function fz at the point z equal to zk. Okay, now let me explain the theorem. Suppose there is the positively oriented closed contour C according to the given diagram. See the given diagram. There is a positively oriented closed contour C and there is a function fz. Okay. Now this function fz is analytic everywhere except at k number of points z1, z2, zk inside C. Okay. Just like the conditions of the previous theorem. There is a function fz. The function fz is analytic on and inside C except k number of points. The k number of points are which? Z1, Z2, Z3 up to Zk. Okay.
স্যার
Yes.
হ্যাঁ স্যার রিয়া বলে কেউ ওয়েটিং রুমে অনেকক্ষণই আছে আর ওর আইডি পাস মানে আইডি আর নাম মানে সব ঠিকই আছে বাট আপনি ওকে অ্যাডমিট করছেন না।
আরে বাবা, এতক্ষণ ধরে যদি সবাই আসতে থাকে আমি অ্যাডমিট করবো না
Sir,
পড়াবো? তো
স্যার ও অনেকক্ষণ ধরে ওয়েটিং রুমে আছে।
ওয়েটিং রুমে 3 জন দেখাচ্ছে এই মুহূর্তে, এবং
রিয়া বলে
3 জনের
ওকে দেখাচ্ছেন।
নেই। ঠিক আছে, এই মুহূর্তে 3 জন আছে, 3 জনের কারোরই নাম আইডি নেই।
ওকে
So let me explain the
আপনি
theorem. Yes. অনেকক্ষণ ক্লাস শুরু হয়ে গেছে, আমি আর কাউকে অ্যাডমিট করব না। এবার ক্লাস শেষ হওয়ার টাইম চলে এলো, আমাকে অলরেডি বলে দিয়েছে যে উই আর রানিং আউট অফ টাইম।
ওকে স্যার।
So there is a closed contour C and a function fz is there. This fz is analytic everywhere, this except some singular points z1, z2, zk. So fz has k number of singular points z1, z2 up to zk, and all these singular points are inside the closed contour C. Okay, if these conditions hold, then the value of the integral fz at fz dz over the closed integral closed contour C will be 2 pi I into residue of fz at the point z equal to z1 plus residue of fz at the point z equal to z2 up to residue of fz at the point z equal to zk. That is the sum of all the residues at the singular points inside C. This thing is nothing but sum of residues at the singular points inside C. So ultimately the value of this integration will be 2 pi I into sum of all the residues at the singular points inside C. So up to this point, if anybody has problem, please tell me.
Sir, what is the difference between this theorem and the theorem before it? Sir, actually, there were also maybe 3 points which were singular, and here are also about k points which are singular. So, for those k points, I am summing them up. Why didn't I sum them up before?
For this theorem, you have to find find the residues at each of the points. At suppose z equal to 1, there is a residue, there is a pole, singular point. You have to find the residue of the function fz at the point z equal to 1. Suppose at z equal to 3, there is a singular point. You have to find the residue at the point z equal to 3. Suppose at z equal to 5, there is a singular point. You have to find the residue at the point z equal to 5. Then sum all these 3 residues. Okay, and then multiply it into 2 pi I for this theorem. But for the previous theorem, you have to find only one residue at the point z equal to 0, and you have to find the residue of the function 1 by z square f of 1 by z, not fz. Here in Cauchy's residue theorem, you are finding the residue of the function fz in all the singular points and then summing it. Then you are adding all those residues. But in the previous theorem, you just have to find one residue, but at the of the function 1 by z square f of 1 by z at the point z equal to 0.
Sir, the result of both the theorem are same.
Yes, obviously. The result will be same.
Okay, sir.
Okay, now we are going to a example, and this example shows that the results will be same. Okay, we are going to the same example as we have used in the previous problem. We are taking the same function fz. We are taking the same function fz. Okay, and we are evaluating the same integral. Okay, so fz is given by this function 5z minus 2 by z into z minus 1, and z equal to 0 and z equal to 1 are two singular points. Okay, now these two singular points are inside the closed curve C. Now by Cauchy's residue theorem, here the value of this integration will be 2 pi I into residue of the function fz at the point z equal to 0 plus residue of the function fz at the point z equal to 1. Here you have two singular points, so you have to find two residues. If you have three singular points, you have to find three residues at those particular points. Okay. Now my task is to find the residue of the function fz at the point z equal to 0. So we are finding z minus 0 into fz at the point z equal to 0 and the value is 2. The residue will be z minus 0. Since we are finding residue at the point z equal to 0, so z minus 0 into fz at the point z equal to 0. This is z minus 0 into fz at the point z equal to 0. The z in the numerator and denominator cancel out. So this is 5z minus 2 by z minus 1 at the point z equal to 0. Putting the value as z equal to 0, we are getting the residue as 2. And this is the residue of the function fz at the point z equal to 1. Since we are finding the residue at the point z equal to 1, so z minus 1 into fz, this is fz at the point z equal to 1. So this z minus 1 and z minus 1 cancel out. So this is a 5z minus 2 by z at the point z equal to 1, and putting the value z equal to 1, we get 3. So the residues are 2 and 3. So finally in this equation we put the values of these residues, this and this, and we get this. That is the 2 pi I into the residue at the point z equal to 0 plus residue at the point z equal to 1. So we get the value 10 pi I. That is the result, same as the previous result. Okay. So you got it?
Yes.
If
sir.
any
Yes, sir.
has problem, you can tell me. Now give me 2 minutes to take the screenshots. Okay, I have got the screenshot of the attendance. Now tell me if anybody has any problem, please tell me.
Sir,
Hmm.
sir, singular points are those at which the function is not defined.
No. That is not the actual definition. Singular points are those points where the function is not analytic. Okay.
सर एनालिटिक का ही तो मतलब होता है कि वो डिफाइंड नहीं है.
नहीं, एनालिटिक का मतलब होता है कि वो डिफरेंशिएबल नहीं है उस पॉइंट में, और उस पॉइंट में और उसका आसपास उसका कोई नेबरहुड में वो डिफरेंशिएबल नहीं है. And
अच्छा,
here
ठीक है.
in of the cases, what's be like if suppose you have 1 by z minus 1. Okay. At z equal to 1, the value of 1 by z minus 1 will goes to infinity. Okay. Whenever for the sake of differentiability, when you are checking to differentiability, you are taking the limit z tends to 1, and at z tends to 1 the value goes to infinity. Okay. So it's actually not different. So the function is not differentiable at that point.
सर कॉची रेसिड्यू थ्योरम के पहले आप जो बताया वो मेरे को समझ में नहीं आया.
सर एक बार
Okay, that's it.
थर्ड पेज
That
पे
is
जाइए ना.
theorem. So you are given a function fz. Okay. Right in your you are given a function fz. Okay.
Yes, sir.
Now function is analytic everywhere except some points in a closed contour. Now draw a closed contour in your copy, and suppose there are more two finite number of points inside the closed contour. At those points the function is not analytic. That is, inside those points, those finite number of points, the function is not analytic. Okay, so those finite number of points are singular points. Yes.
Yes.
Okay, So fz is a function which is analytic everywhere but some finite number of points, and all those finite number of points are inside the closed contour. That is, all the singularities of the function fz is inside the closed contour.
Yes, sir.
Okay, if these conditions hold, if these things hold, then the integration of the function fz over the closed contour C, if I name that closed contour C, this will be, the value of this integration will be the residue at z equal to 0 of the function 1 by z square f of 1 by z. Okay, you are given the function fz, but the residue will be of the function 1 by z square f of 1 by z at the point z equal to 0. Okay. This
Okay, sir.
value of the integration and the value of this residue will be same. The integral value will be the same of the residual value at the point z equal to 0 of the function 1 by z square f of 1 by z. Okay.
सर एक बार पेज नंबर 3 में जाइए ना.
Okay, page number 3. 1 2 3. हाँ, बोलो, बताओ.
सर ये वाला जो आप लिखे हैं ना, ये वाला कैसे किए सर?
Okay. This line.
यस सर.
सर
You
अभी
are
तो आप
asking
यही बताए ना.
हाँ?
अभी तो सर आप यही बता रहे थे ना कि अगर एफ जेड एनालिटिक है सारी जगह में तो उसका फाइनाइट पॉइंट्स क्लोज कंटूर्स के अंदर होगा, तो इंटीग्रेशन ऑफ एफ ऑफ जेड उस कंटूर पे वो आपका रेसिड्यू एट जेड टेंड्स टू 0 1 by z square into f of 1 by z.
Z tends to 0. Residue of the function 1 by z square f of 1 by z at the point z equal to 0. Okay.
हाँ
सर तो ये
So,
वाला जो
here-
वैल्यू है ये तो वो
देखो।
एफ ऑफ 1 by z स्क्वायर का वैल्यू है ना, और सर एफ ऑफ 1 by z का वैल्यू
The value on this value is this value. This is finally 1 by z square f of 1 by z. This value is this. I have calculated in the previous. Okay, let me go there. Previous page. You were given z. See here, you are given fz. Fz is 5z minus 2 by z in z minus 1. But find the residual value at point 1 by of the 1 by z square fz. Sorry, f of 1 by z. This is a simple printing mistake. This will be 1 by z square into f of 1 by z. Okay. So my connection. Okay. So second page. So the function is given by this j into 1 by f is equal to 5z minus 2 by j into z minus 1. But first we have to find the function 1 z square f of 1 by z. This will be f of 1 by z. So how we find first f of 1 by z? By replacing z by 1 by z. In the function fz, we are replacing z
हाँ
by
सर
1
समझ
by
गया
z.
समझ गया.
Here we are replacing z by 1 by z and get this. And 1 by z square will be this thing.
Yes,
right?
हाँ समझ गया. हाँ
Okay. Any other problem? So this is a doubt sharing, doubt clearing class. If anybody has any problem, tell me. So I think there is no problem at all. Nobody is funding. So I think the class is done.
सर हम लोग रेसिड्यू तो सिंगुलर पॉइंट्स पे निकाल रहे हैं, तो यहाँ पे तो सर सिंगुलर पॉइंट्स दो था 0 और 1. तो यहाँ पे सिर्फ एक ही बार 0 के साथ हुआ है, 1 के साथ नहीं हुआ।
वही तो बात है, दिस प्रीवियस थ्योरम में ओनली यू हैव टू फाइंड द रेसिड्यू ओनली एट द पॉइंट z equal to 0.
अच्छा, ओके सर।
But in Cauchy's residue theorem, you have to find the residues on all the
एवरी पॉइंट।
at every and there is another more difference. In Cauchy's residue theorem, you have to find the residues on all the singular points, but of the function fz. Of the function fj. But here in the previous theorem, you have to find the residue at the point z equal to 0, but of the function 1 by z square f of 1 by z. The functions are different now.
समझ गए।
That is the difference. Any other problem?
No, sir.
Okay.